Okay, so let's start for today. So we had seen till now uh, the three regions. Okay, can you remember those three regions? We had seen the condition, then we saw the depletion region condition, and how does a depletion region is formed. Okay, when we apply a small positive voltage at the gate, then if we increase the voltage intensity, then increase the voltage magnitude, keeping it positive, okay, it will result in an inversion layer. Okay, so this is the main concern here, because inversion layer means the conducting layer, that is formed between source and drain, and this will help us to make a current to flow between source and drain terminals in a MOSFET structure. Okay, so now there is a derivation required here in this case under depletion region. Okay, now see here that when a depletion region is formed, okay, when we apply a small positive gate voltage, okay, where is this cursor? Okay, look at this. A small positive gate voltage is applied at the gate terminal. And in that case, this is the depletion region that is formed in the p-type substrate, p-type substrate area. Okay, and there is a derivation that is there for calculating the thickness. That is this thickness of the depletion region. Okay, and how thick the depletion region is formed. Okay, so let us see how does the derivation goes. I have taken this photo from my copy from my notes itself. Okay, the photo has not come that with that brightness, but I think it is still readable. So because the typing all the things, all the equations takes a lot of time. So I thought, let me go by taking a photo of this. Okay. So calculation of depletion width, and keep that image in your mind that what are we going to calculate here. We are going to calculate the width of the depletion or the depth of the depletion region that is formed under depletion mode. Okay. So let us consider a small portion in the depletion region of length dx and charge dq. Okay. So this will be derived with the help of integration. Okay. And we know the concept of integration, that we take a small portion of that any particular area, okay, and then we try to integrate that, try to perform integration on that particular small chosen region. Okay, and the limit of the integration would be the boundary condition provided by that particular area, uh, whose dimensions we already know. Okay, so here we want to calculate the depth of the depletion region. Okay, and we know certain boundary conditions for that depletion region. Okay, and we will use those boundary conditions to apply the limits on the integration. So let's start that. Let's consider a small portion of the depletion region, and let's name this as a dx of thickness of dx. Okay, or the length dx, and let's say that it contains a charge, a very small charge, dq. Okay, now for that particular small region dx, we can write the equation for dq, that is the charge contained in that particular small region, as minus q dot na dot dx. Okay, minus. Why minus? Because this depletion region consists of ions. Okay, what kind of ions? Acceptor ions. Acceptor ions basically. And when acceptor ions accept one electron from outside, they become negative, negatively charged. Okay, and this is why this negative sign is coming here. Q is the charge, uh, unit of one, unit of one charge. We know that thing. So this is charge that will be expressed in coulombs. Okay, Na is the concentration of acceptor atoms, acceptor impurity, that is used for creating N type substrate. And remember, this is for N MOSFET. This derivation is applicable to N MOSFET device. Okay, and for N MOSFET device, we need a substrate or bulk or body of what kind of semiconductor? Basically, P-type semiconductor. Okay, so and for forming a P-type semiconductor, we usually dope it with acceptor acceptor atoms. Okay, and this is the same acceptor concentration that is used for forming a p-type semiconductor or a p-type substrate. Okay, and dx is the length of that particular region. Okay, now if you calculate the dimension for dq from here, it will come like this. Q is coulomb. So basically, if I can write here, uh, okay, Q is for coulomb, and Na is actually the concentration is uh, simply expressed in terms of number of charge carriers per unit area. So we can write this, the unit for Na would be, let's say, the number of charge carriers per centimeter cube of volume. Okay, and dx would be the length of that particular region, and this will be in centimeter. Okay, so this centimeter will cancel with this cm cube, and it will remain with, it will be left with cm square. Okay, so this will basically result in a unit of coulomb per centimeter square or meter square. Okay, centimeter square or meter square. This C is for coulomb. Okay, and this cm is actually centimeter. It can be a meter. Okay, it can be meter. Okay, so do not get confused. Basically, centimeter square means that it's a surface. It's a two-dimensional surface. It can be centimeter square, it can be meter square, or it can be micrometer square, depending on the choice that the designer takes. Okay, so the unit for dq will come out to be in terms of like coulomb per meter square. Okay, so coulomb per meter square. So the coulomb per unit area, this centimeter square or meter square denotes the area. Okay, so this will look like a charge sheet. The charge sheet, okay, uh, parallel to the surface, parallel to the surface. Okay, why are we calling this as a charge sheet? Because this is spread in terms of this with this dimension, that is per centimeter square. Okay, so one thing is clear, that this dq is not simply coulomb. This, the unit for this dq is coulomb per centimeter square. Okay, so keep this thing in mind, and bring this dx on the left hand side. This will become dq by dx, and on the right hand side we will be left with minus q dot na. Okay, and this is what actually coulomb na, the unit of na is per meter cube. Okay, so this will be coulomb per meter cube. Okay, and we can call this by a single uh, term, let's say rho. Okay, and rho will denote the charge density in terms of per meter cube of area. Okay, now we will use Poisson's equation here for deriving the depletion width And the statement of Poisson's equation is this one, that it relates the rate of change of voltage, okay, with the charge density. This is the characteristic of Poisson's equation. That is, it establishes a relation between the rate of change of voltage with respect to distance with the charge density rho here. Okay, so this statement is universal. This is given as d square v by dx square, that is d square v is for voltage and x is for distance. So this is double the rate of change of volt with respect to distance, and this is equal to minus rho by epsilon si, epsilon silicon, where rho is the charge density that is there in that particular region, and epsilon of si denotes the dielectric constant for silicon, because we are calculating the depletion width that has been formed in the silicon, in the p-type silicon substrate. Okay, and hence the epsilon for silicon value would be used here. Okay, so this is the statement for Poisson's equation. Now, the potential at the oxide depletion layer, the potential at the oxide depletion layer interface is surface potential. Okay, and the potential at the depletion layer and the semiconductor interface is the Fermi potential. Okay, now if we can go, if let me go to that diagram, look at here. So there are basically two surfaces here. There is one surface that exists between the oxide and the semiconductor. This is the first surface, the first boundary for the depletion region, and this is the second boundary for depletion region. Okay, and this is the surface that exists between the depletion region, okay, and the p-type silicon substrate. Okay, and these two regions are basically being referred here. So look at this, the first region, that is oxide and depletion layer interface, and this potential at this layer, at this interface, let's call this as the surface potential, that is phi s, and the potential at the depletion layer and semiconductor interface, let's call this as the Fermi potential phi f. Okay, so we have got the two boundary conditions that exist for this depletion layer. Okay, and we know that these two boundaries will be at different potential, right? Because this is, after all, this is all because of the difference in potential that exists in the structure, and which is responsible for all these phenomena. Okay, so let's call the potential at the top interface as surface potential, and at the bottom boundary as Fermi potential phi f. Okay, so this uh, Poisson's equation, Poisson's equation, if we apply at the top interface, that v would be should be replaced by phi s, that is the surface potential. Okay, so this becomes d square phi s by dx square equals to minus rho by epsilon silicon, epsilon si. Okay, and this can be written as d square phi s by dx square, that is equal to q n a by epsilon. Can we write this? Look at, we had here this rho was actually equals to minus q n a. So substitute this term here in this equation. This will become like this, q dot n a by epsilon si. Okay, these are simple substitutions. So we are left with this equation. Okay, apply one differentiation over here, sorry, one integration over here. So this will becomes d phi s by dx. Okay, integration. So, and we will be left with okay, d phi s by dx, and this is changing with respect to dx. Okay, and a new term x will come here because the integration will be performed with respect to x. Okay, this is visible from here. Okay, dx square, so this is with respect to dx, and when you perform one integration here, the integration of that particular dx will result in one extra term, that is x. Okay, now we can bring this dx on the right hand side. So d phi s will be equal to this term into dx. Okay, now let's apply integration for one more time. So integration of d phi s, that is the surface potential, okay, would be equal to the integration of this right hand side whole term. Okay, that is q n a x by epsilon si dot dx. Now here the variable that is changing is phi s d phi s. Okay, and the boundary condition for d phi s we had just seen is from the Fermi level to the surface level potential. Okay, so there was one Fermi potential, if you can remember from that diagram. Let me go to that. Look at here. So this was at Fermi potential, and this was at surface potential. So this is integrating from phi f to phi s. Okay, and this is what is the limit that is set here in this integration. The limit from lower limit, that is phi f, to higher limit, that is phi s over here. Okay, and here the variable is dx. So let's say it start from 0. The thickness of depletion region is, let's say, start from 0, that is the bottom or the upper layer. Okay, and the other interface is at some thickness, some distance apart, away from the first interface. Let's say this is xd. Okay, where xd denotes the depletion region thickness. Xd is the thickness of depletion region. Okay, perform the integration here. This will result in phi s minus phi f, that will be equal to, and this is x dot dx, so this will be x square by 2, and when we apply the limits here, this will be equals to xd square minus 0, that is xd square here. So it becomes q dot na dot xd square by 2 epsilon si. Okay, from this equation we can calculate the value for xd easily. So xd square will be uh, expressed in this, with this term, and when you calculate the value for xd, it will be the square root of this whole term, and xd will be given as the square root of 2 epsilon si mod phi s minus phi f by q dot na. Okay, okay, so this is the expression for the thickness of depletion region, right? So can we analyze this equation further, that on what parameters does this depletion region thickness depend? Look at here. 2 is a constant. Epsilon si is actually the dielectric constant of silicon material. This is also a constant. Okay. Q is charge, that is again a constant. Phi s minus phi f, and Na is the doping density of that particular silicon material. Now this doping density may vary. Okay, this doping density would vary according to the design, according to the actual doping that is done actually. Okay, but in most of the cases you will find that the value of Na is somewhere around 10 to the power 16 per centimeter cube. 10 to the power 16 per centimeter cube. This is a typical value that I am saying. Okay. So when you increase the doping density, the depletion thickness decreases. Okay. And then the phi s, the surface potential, minus phi f, that is the Fermi potential. So this is directly depending on the difference of phi s and phi f. Okay, so this was clearly visible because we attached phi s to the top interface and phi f to the bottom interface. Okay, so the main parameter that is controlling the thickness of depletion region here is Na, that is the doping density of the silicon semiconductor substrate. Okay. Okay, so this is the equation for xd, that is depletion region. Okay, now we can calculate the we can also calculate the charge content of that particular depletion region. That is, what is the total charge that is there inside the depletion region area. So the total charge content of the depletion region. Now the total charge in depletion layer. Okay, we have this equation. We had already this equation from equation number 7. Okay, so from this we got this dx will come here and dq will be q minus q dot na dot dx, right? And q equals to minus q dot na dot x. Okay, perform one time integration here. This will be like this. Okay, now this q contains the term x, where x is the variable that denotes, that is associated with the thickness of the depletion region. X can be anything between 0 and xd, remember. Okay, so at x is equal to xd, at x is equal to xd, that is the maximum value of x could be xd, the thickness of the depletion region. Okay, so when we put the maximum value in this particular equation, this will result me the maximum charge content in the depletion region. Okay, and then we had already seen the equation for xd. Put up the value for xd, the term for xd here, and it will be like this. It will look like this. Rearrange this term, simplify this, and we can then easily show that the total charge content of the depletion region would be minus square root of 2 epsilon si mod of phi s minus phi f dot q dot na. So again, what is the parameter? What are the parameters on which the total charge content is depending? Epsilon si would be a constant. Q is a constant. This will also be this will actually depend on the external voltage applied. Okay, that is Vg. Okay, so this is one parameter, and Na, the doping density of the silicon substrate, p-type silicon. So this Na and phi s minus phi f are the two parameters that will on which, and they are directly proportional, they are directly affecting the value of charge content q. Okay, so this q will depend on two parameters here. One is Na and the other one is phi s minus phi f. Okay, so here we had seen the derivations for the depletion region thickness, that is xd, and the derivation for the charge contained in that particular depletion region. Okay, the charge contained in that particular depletion region. Okay, now these are simple formulas, and you may find some small numericals based on these formulas. Okay, Okay, so that was a derivation that was related to the formation of depletion layer. Okay, now remember again, I'm always saying that those three modes, those three regions are very, very important. What were those three states? The first one was uh, accumulation region, the second one was depletion region, and the third one was inversion region. Okay, accumulation, accumulation of majority charge carriers, then depletion region formation, and then inversion. Inversion was actually the accumulation of minority charge carriers. Okay, so look at here again. I am showing here physical structure of an N channel enhancement type MOSFET. Okay, now you should be able to differentiate by looking at the structure that what kind of MOSFET it is, whether it is an N channel MOSFET or a P channel MOSFET, or also whether it's an enhancement type MOSFET or depletion type MOSFET. Okay, now I have uh, these two terms I have typed with a different color, the N channel and the enhancement type. Look, again I am saying that this p-type silicon is used for creating n MOSFET, n channel MOSFET, and vice versa. Okay, or you can also relate it with the source and drain. The source is n plus, it means that it's a n channel MOSFET. The drain is n plus, it means that it's a n channel MOSFET. Okay, so either way you can remember here. Okay, and this is the metal layer. Okay, this is the oxide layer, and this is the semiconductor region, semiconductor layer. Okay, and we have a source here n plus, and we have a drain here n plus, and the channel is the length, the least the least distance between the source and the drain, between the source and the drain, and this is actually there uh, present near the interface between the oxide and the silicon substrate. Okay, so this particular distance from this point to this point is called the channel length for this particular n channel MOSFET, and this is enhancement type. Enhancement type means what? It means that there is some kind of enhancement in the operation of MOSFET. So what enhancement is observed? The enhancement means an increase. Okay, the literal meaning of enhancement is to increase something. Now here there is an increase, or there is an enhancement, or there is an appearance of channel. The channel appears when we apply a suitable voltage at the gate terminal. Okay, when nothing is applied here, there is no existence of any channel between source and drain. But when we apply a suitable voltage here at the gate terminal, then we observe that an inversion layer is formed, or a channel is formed that connects the source and the drain region. Okay, and this channel that will be formed here will be of n type, and hence this will match this n plus region to this n plus region via its n type channel formation. Okay, and because this channel is formed, earlier it was 0, and after some time it became some, it appeared, it got enhanced. Okay, because of the application of a suitable voltage at the gate. Okay, and because of this phenomena we call this as an enhancement type MOSFET. Okay, there is another kind of MOSFET that is called as a depletion type MOSFET. So what happens in depletion type MOSFET is that there is a phenomena, like we can say that it depletes. Depletion of what? Depletion of the channel. So all these things are related to the channel, the enhancement of channel or the depletion of channel. Okay, now in the case of depletion type MOSFET, the channel would already be implanted, would already be fabricated there, the channel would already exist. Okay, the channel will already exist. Now after application of a suitable voltage at the gate terminal, we would try to deplete the channel that already exists. Okay, and it means that as the channel gets depleted, the connection between source and drain uh, becomes weaker and weaker, and at some point we we lose the connection between source and drain. Okay, and that particular thing, that particular voltage value will be the threshold voltage for that particular depletion type MOSFET. Okay, so get the difference, know the difference between enhancement type and depletion type MOSFET. Okay, and this structure you should remember, this is a very simple structure, and there are some points regarding this. Okay, again, this is the channel length of the channel that exists between source and drain. Okay, and this is actually a three-dimensional device. Okay, and hence this is the channel width of the channel that is there between source and drain. Okay, now in this case the channel width is equal to the dimension of this particular source, that is from here to here, or the dimension of this particular drain, that is that extends from here to here. Okay, so these all are equal to the channel width, and in most of the cases you will find that the value of channel width, that is W, is usually higher, bigger in value as compared to the channel length, that is L. Okay, and the ratio of W by L, that is channel width to channel length, is a very important, is a very important design factor in the designing of these MOSFETs. Okay, so this is the simple physical structure of n channel enhancement type MOSFET. So what are the points? This MOS structure consists of one polysilicon gate, a thin oxide layer, and then a semiconductor layer. We know this thing. Okay, all the things that I have told, those same things are written here. The source and drain are n plus regions. N plus means it is heavily doped, and wherever you see n minus, it means that that is n type, but thin, very thin doping, not that heavy doping is there. So plus is for heavy doping, minus is for weak doping. Okay, and n is normal. Wherever you see n without any plus or minus, it means that it's a normal doping. The current conducting terminals of the device are source and drain. Okay, and in between exists a conducting channel. The channel length is L and the channel width is W. Okay, the device structure is completely symmetrical with respect to the drain and source. Now remember, the device structure is symmetrical in nature. It means that if I draw a line in between, a vertical line here in between this structure, then we can see a symmetry between the left hand side and the right hand side, and also we can interchange the terminals. So it means that we can use this particular terminal as drain, and we can use this particular terminal as source. Okay, so the two terminals are interchangeable in nature. We can use either of these terminals as a source or drain. It is not restricted, as in the case of BJT. In BJT, it was not a symmetrical device. Okay, the terminals, that is base, collector and emitter, were fixed. You cannot interchange the collector and emitter terminal, but here you can interchange, we can interchangeably use the terminals of source and drain. Okay, and the most important thing is the operation of the device. Okay, look at here. The operation of this device is actually because of that effect, we call this as a field effect, FET, field effect transistor. Okay, what is this field effect operation? Is that the controlling of the current conduction between source and the drain. Okay, remember that the current will flow between source and drain, and how do we control that current between source and drain? Is by using the electric field Okay, and this field is generated by the gate voltage as a control variable. Okay, so when we apply a gate voltage at the gate terminal, there is a formation of electric field in this region. Okay, and this because of the effect of this electric field effect that uh, controls the flow of electric current between source and drain. Okay, and this is the whole operation. This is the whole operation of this particular MOS device. So remember this operation, that how do we control the current conduction between source and drain. Okay, and then it will help in understanding the other operations, the other things related to this MOSFET device. Okay, so till this point, any doubts, anything from the students? I hope the students are listening, because I'm here speaking alone, but I cannot, monitor you. I cannot see you that whether you are paying attention or not. So whenever I ask something, at least respond at that time. Okay. Or if there is any doubt, you can ask that doubt at any time in the lecture. Okay. Uh, Now, this is the symbols, the circuit symbols for enhancement type MOSFET. Look at this. So let's start with the N-channel MOSFET. Okay, all the things will be there with respect to N-channel MOSFET. Okay, and the derivation for the respective P-channel MOSFET can be done by just changing the polarity of the voltages that are there in the equations. Okay, so if you want to migrate between N channel to P channel, it is very easy. All the equations will be valid. All the equations will be valid, but only there will be a change in the polarity of the voltages. That's it, and nothing, and no other parameters will change. Okay. So N channel MOSFET means there is a N channel existing between source and drain. Okay, and we know that MOSFET is particularly a four terminal device. The four terminals are the gate, the source, the drain, and the body. Okay, look at here in this diagram again. This is the gate terminal, this is the source terminal, this is the drain terminal, and this is the body or the substrate or the bulk terminal, body terminal. Okay, the fourth. Okay, now to make it simple, many times you will see that this particular symbol would be dropped and this symbol would be used, that the arrow comes down here and comes here, the outside coming arrow on the source terminal. Okay, now the arrow will always be drawn on the source terminal. Remember this point, the arrow will be present only on the source terminal, like in the case of BJT, the arrow was present only on the emitter terminal. Okay, similarly here in the case of MOSFET, the arrow will be present on the source terminal always, and there is a gap between gate and this channel. This is the channel that is connecting the source and drain. Okay, and this particular layer represents that particular MOS layer. Okay, we can say that this is the first line is for M metal, the gap between two lines is the oxide layer, and this second line is the semiconductor or the channel. Okay, so this particular structure actually is symbolic to MOS. In many cases you will see that even this symbol, even this arrow is also dropped. Okay, so there is no necessity of drawing the arrow. It will become even simpler, just this structure and this gate, because we know that the source and drain terminals are they can be interchangeably used. Okay, this structure is a symmetrical structure. Okay, but there should be one point that should be kept in mind, that the body terminal and source terminal are are connected to the same potential. So in this case, it is conveying the message that the source terminal and body terminal are connected to the same potential. This point should be kept in mind. Okay, and if it is not so, if the body terminal is not connected to the source terminal, then in those cases, the body terminal will be shown with a with that fourth terminal that is connected to some different potential. But if it is connected to the source at the same potential, which is the case in most of the times, okay, in those situations you will not see the fourth body terminal and the arrow. It is understood automatically. Okay, so keep that thing in mind. Now similarly, we can go with the p channel MOSFET. The only difference would be the direction of arrow. Okay, in this case the direction of arrow would be pointing outwards, and this is pointing inwards. But one thing is common again is that the body is connected to the source at the same potential. It is understood here the body is connected to the source at the same potential. If it is not so, it should be shown separately here. So unless it is not shown separately, we can assume that the body and the source are connected, the terminals are connected to the same potential. Okay, so we will see this particular symbol for NMOS and this particular symbol for PMOS. The difference between these two symbols is the existence of this small circle at the gate terminal. Look at here. Okay, so this small circle at the gate terminal differentiate the symbol for this particular P MOSFET than that of this N MOSFET. Okay. Okay, so these are the symbols for NMOS and P MOSFETs, and these are enhancement types. These are enhancement types. And when you go for the depletion type MOSFETs, you will see that there is a dashed line present between drain and source. That, but here, because here we are seeing a continuous line, but in the case of depletion MOSFET you will see the dashed line, a broken line. So that broken line will signify the depletion of the channel when a suitable voltage is applied. Okay, so these are the same things that I have told here. Okay, so we will resume from here. Please give your attendance in the chat box. Write your roll number and name. First write your roll number, then your name.